Today, we are going to talk about the frequency response of cascode amplifiers. And we are going to constrain our investigation to high frequency because cascodes are typically integrated or implemented as an integrated circuit, and so it's going to be the parasitic capacitances that are going to overwhelmingly affect the behavior. We are going to continue to look at these circuits with channel length modulation neglected, which, if I'm being honest, the only reason we're doing that is because I didn't realize that's how I did my notes last year. To me, it doesn't make a great amount of sense because cascodes depend on having or utilizing channel length modulation for our resistance R naughts, but I didn't realize until too late that that's not how I had structured my notes last year to match what Dr. Batari is doing. So for now, we're just going to go with this. Okay. Couldn't give you a better reason than that, unfortunately. So for our cascode amplifier, we're going to have something that looks like this. So here's VDD. We are biasing our cascode with some resistance RD. And then right here is where the drain of our transistor 2 is. And then we have our connection to transistor 1, like so. And let's start filling some things in here. So for transistor M2, we are going to have our gate drain capacitance, CGD2, like so. Our gate source capacitance, CGS2, like so. Our source bulk capacitance, CSB2. And then from the drain to the bulk, we will also have our capacitance EDB2. And then here is where our output voltage is taken at the drain terminal of transistor M2. Our gate terminal of M2, if you recall, is at some DC bias voltage, which will look like an AC ground. We'll get to that momentarily. For transistor M1, we have our gate drain capacitance, CGD1, our gate source capacitance, CGS1, our drain body capacitance, CDB2, our source body capacitance, CSB2, our source terminal for transistor M2, or excuse me, transistor M1 is grounded, and we apply our input voltage. All right, so let's take a look at this horrifying mess of capacitors and see what goes away. All right. So capacitance CSB2 is out, right? It's grounded on both sides, so we don't really have any issue there with canceling that guy out. So I'm just going to put red X through it. CDB2 is going to exist, but we can see that CGB2 should be in parallel with CDB2 if we're treating this V bias as an AC ground. So on our output node here, what we should see is CGB2 in parallel with CDB2 in parallel with this resistance RD. So we have kind of a discrete impedance associated with that output node. Let's see. At this node here in the middle, we're going to have CSB2 in parallel with CGS2. Since V bias is AC ground, they both share the source of M2 and ground. CGS2, CSB2, and CDB2, that'll be in parallel as well. CGS1 is between the input node and ground, so that's going to be by itself. And then CGD2 is going to be the real pain in the butt to deal with because it's providing feedback between our gate and drain for transistor M1. So if we drew a small signal model of this guy, what we would have is something that looks like this. So I'm starting with transistor M2. So this is my gate node for transistor M2. Here I have VGS2. Down here is my source node for transistor M2. GM, VHG2 in parallel, or excuse me, not in parallel. And then connected here will be some impedance. Let's call it RD in parallel with C out, where C out is simply CGD2 plus CDB2. And here is our output node. All this up here represents the drain of transistor M2. Down here, we're going to have transistor M1. So this is our drain of 1. We have our dependent source, GM1, VGS1, in parallel with the capacitance. I'm going to call this CY, and this is C. Oh, I mislabeled that. That's why I was confused. This should be CDB1 since it's for transistor M1. I apologize about that. CDB1 in parallel with CGS2 in parallel with CSB2. Our source node here is at ground. We have our capacitance CGS1 here, over which a voltage drop VGS1 occurs. And then let's call this our input voltage, Vn like so. Here's our capacitance CGD1. and then our source of 2 and our drain of 1 are tied together. So I believe that's what we're looking at, this mess of stuff. All right, so let's begin. It's lots of, yes, sir.
What is that subscript on that capacitor to the bottom line?
This guy right here, the letter Y. So I'm going to call this node Y and this node X. And so that's why I'm going to call that CY, because it's the capacitance connected between node Y and ground. All right, so if we do KCL at node X, we are going to have the current flowing through that capacitance CGS1. So that's going to look like S CGS1 times Vx plus S CGD1 times Vx minus Vy is equal to 0. And so all I'm going to do here is just kind of split things up a little bit. So it's going to look like S CGS1 plus CGD1 Vx is equal to S CGD1 Vy, and I'm trying to decide which way I want to do this here real quick. Let's say that, actually, let's leave it like that for now. Sorry, we're going to come back and probably make one simplification here, but I'm not sure how it's going to go just yet. I'm either going to put everything with Vx on one side or everything with Vy on one side. It's obviously one algebraic step to go either way. So I'll come back and revisit that momentarily. All right. Now we're going to apply KCL at node Y. So we have a current flowing to the left through our capacitance CGD1. So that's going to look like S CGD1. Sorry, there should not be a parentheses here. S CGD1 Vy minus Vx plus GM1 times VGS1, which is the exact same thing as Vx, plus SCY times Vy. So that's the current flowing down through this capacitance CY. And then the last thing I have is a current flowing in, which is GM VGS2. Okay. So ostensibly negative GM2 VGS2. I need to pay attention to that, my apologies. But we can notice pretty easily that VGS2 is negative Vy, right? So negative GM2 times negative Vy looks like positive GM2 Vy. So, and we're gonna group things up here as well, okay? So for my Vx bit, let's see, let's put the Vy stuff on the left-hand side. So we're gonna have S times CGD1 plus CY plus GM2 times Vy is equal to negative GM1 plus S CGD1 Vx. So with simple algebraic manipulation here, we can kind of choose our own adventure at this point. We have isolated Vx and Vy in this equation. We have isolated Vx and Vy in this equation. So it's just going to be a combination of these two things multiplied together, giving us our transfer function Vy over Vx. So I'm going to take this guy and make everything in terms of Vx, okay? So Vx will be S CGD1 over S CGS1 plus CGD1 multiplied by Vy. I'm actually running into a bit of an issue here. Sorry. Boop, boop, ba-doop. Let me think about this for just a moment here. So I know that Vx is my input voltage. But I'm getting two different transfer functions that are going to relate Vy to Vx. Now, I know actually that this is supposed to give me a second order polynomial. So I'm confused as to why that isn't happening, to put it bluntly here. So let me double check my math here. Okay, so I have.
Is there a current coming in for being?
Yeah, I think I think actually that is absolutely the issue, is that there's a path there. And I could quantify that by just putting an arbitrary signal resistance in there to give me a voltage drop that I think I might need to do. Because when we applied KCL right here, I think you're 100% right. When we applied KCL right here, we took this current flowing down, this current flowing to the right. We did not take into account that there could be Vx. Effectively, there could be current being input into the system by the input voltage. So let's modify this slightly. I'm just going to throw a resistance that I'm going to call R sig right here. And that's going to change these relationships. I apologize for not noticing that earlier. So that's going to look like Vx minus Vn over R sig right there. That's going to change this relationship slightly and this relationship. So sorry for the boneheaded mistake, you guys. This is equal to 0. So my Vx term is going to look like 1 over R sig plus S CGS1 plus CGD1, all of this times Vx minus SCGD1 Vy is equal to Vn over R sig. Okay, now we're going to have a second order equation fall out of this when I do the substitution. All right, thank you for that, Andrew, I believe. Yes. All right, so let's make sure the math from here to here makes sense. Let's start there. Apologize again for my mistake. So we're at this point. I can algebraically manipulate this to put everything in terms of Vx, substitute that into here, and I have a relationship between Vn and Vy, which is absolutely what I'm looking for. Great. Thank you for your help. So from here, we would have Vx is equal to GM2 plus S CGD1 plus CY divided by negative GM1 plus S CGD1. Do I need to go back and look at something? Are we good?
No, sir.
Okay. So let's just double check that math there because I'm feeling conscientious about things because I've made a mistake. So GM2 plus S CGD1 plus CY. So that seems legit. Negative GM1 plus S CGD1. And that should be in my denominator, giving me everything is equal to Vx. Okay. So I'm going to substitute this relationships for Vx into my original equation. And so what that's going to give me is Vn over R sig is equal to, let's see, 1 over R sig plus S CGS1 plus CGD1 times Vx. So I'm literally just substituting in what I have up here. GM2 plus S CGD1 plus CY all over negative GM1 plus S CGD1. And then I have that minus CY term here. So minus SCGD1. Vy. All right, so what will we need to do next? Well, oh, and there should be a Vy here. Making all kinds of mistakes today. All right. So let's talk about what we should be doing right here, okay? So one thing that I could do that would make my life a little bit easier right now would be to multiply everything through by a factor of R6, right? that'll clear this fraction. It'll put a bunch of r's in places, which isn't necessarily a bad thing, but it's going to make it a little easier to figure out what Vy over Vn is if I don't have all those fractions in place. So step one, let's multiply through by r sig. So this is giving us Vn is equal to 1 plus s r sig CGS1 plus CGD1 and then up here I'm going to have GM2 r sig plus s r sig CGD1 plus CY. My denominator is going to stay the same, negative GM1 plus S CGD1. Then I have a VY, and then I'm going to have a minus S R sig CGD1 VY. The next thing I need to do then is lump this together so that I have everything multiplied by a single term of Vy, right? So the easiest way that I can think of for me to do this would be to multiply this bit right here by a factor of this denominator over this denominator so that everything has the same common denominator and I can just lump it all together. Does that seem reasonable? All right. So that's going to look like, let's see here. I have 1 plus S R sig CGS1 plus CGD1 times GM2 R sig plus S R sig CGD1 plus CY minus S R sig CGD1 multiplied by negative GM1 plus S CGD1 and this whole thing over negative G1 or GM1 plus S CGD1 multiplied by a factor of Vy. Okay, so all right. So obviously I have an S bit times an S bit here, so it's going to give me an S squared times some stuff. I have an S bit here multiplied by an S bit here, so I'm going to have an S squared. So this is going to combine together to look like a second order polynomial for my transfer function just between Vy and Vn. My pole frequency is going to come from this part right here. My zero frequency is going to come from this part right here. This part up here is going to be associated with two poles. Do we want to go through the algebra of figuring out what that is and spend the rest of the class period on that, or do we want to move on?
Moving on sounds good.
Okay. Yeah. Well, with your homework assignment, I hope at this point that you would know how to lump all that stuff together, because that's a big part of homework 3 problem 1, and excuse me, homework 4 problem 3A. Is effectively taking a big ugly expression like this and then making it look like a second degree polynomial function. All right, so we can see from here where our transfer function is coming from. Can we at least agree on that part? Okay. Are you humoring me? Probably. Okay. So all we're looking for this part is to get a relationship between Vy and Vn. So Vn is equal to all this crap multiplied by Vy. So Vy over Vn is literally just flipping this fraction upside down. So we have a 0 and then 2 poles. All right. If we perform KCL at our output node, so this is going to give us, I'm just going to write that down. 1 pole and 2 poles and 1 0. One zero from this. So very similar to what we had for, at least in scope and everything, with what we did with our common source amplifier when node, the gate node and the drain node were linked together. So if we perform KCL at our output node, let's look at what that's going to look like real quick here. All right, so at our output node, double check my notes because I'm feeling unsure about myself here. Okay. So we're going to have current of V out over RD flowing out, the current of V out times SC out flowing out, and then the current of GM times negative VY flowing out. So this is going to give us a transfer function between node Y, this source drain combination, and our output voltage. Okay, so that's working as expected. So KCL at the output node should look like SC out, V out, plus V out over RD minus GM2 VY is equal to 0. So we can pull all the V out terms on one side and the VY terms on the other side. So that's going to look like 1 over RD plus SC out times V out is equal to GM2 VY. Let's multiply both sides through by RD, giving us 1 plus SRD V out times V out is equal to GM2 RD VY. And then finally, V out over VY is equal to GM2 RD over 1 plus SRD C out. And that's where our third pole is going to come from. So from here, we've definitely determined at least where one of our poles is going to come from for sure. We know what one of our 0 frequencies is, or actually our only 0 frequency. And our other 2 poles are going to come from combining this into a second order polynomial and then applying quadratic equation, negative b plus or minus the square root of b squared minus 4ac. That's a quadratic equation, right? Sorry, my brain is just absolutely melted today, apparently. I don't know what the hell I'm doing. So this is our analysis for a Cascode amplifier, which I feel very strongly I'm going to go redo in my office and then just post notes that make some damn sense to you guys later on today, so that we just didn't completely waste a bunch of time. All right, so this would be doing it the hard way, okay? We could also break things down using that Miller method again, okay? So if we were so inclined, which based on the absolute jackassery amount of mistakes I'm making today, I don't trust my notes. But if we were so inclined, we could split this capacitance CGD1 up here and put a portion of it in parallel with CGS1 and put a portion of it in parallel with with CY. Now the question here would be, what would our transfer function between node X and Y be? And this is going to be something that we haven't seen before because we're neglecting the effects of channel length modulation, right? So let's talk our way through that. So if I had the following circuit. Here's RD. Here's my bias voltage, V bias. Here's my input voltage. This is node X, and this is node Y, for our DC circuit representation, right? So this is how we would figure out what that transfer function is in order to apply the Miller technique here. Let's put it over here like so. So AV XY, let's talk about that, right? So that's our voltage gain between node X and node Y, which is simply the ratio VY over VX, right? The easiest way, I think, that we could do this would be to utilize that short circuit transconductance technique that we've done previously, okay? Where we would have capital or negative capital GM multiplied by the output resistance seen looking in here, because that's exactly what we're trying to find is that relationship between those two nodes, right? Which is the voltage gain of this system as we've drawn it. So what we have down here at the bottom, I draw my arrow here to make it obvious, is a common source amplifier that is being loaded by this PMOS, or excuse me, being loaded by an NMOS current source that is being generated by a resistance RD. So what should the short circuit transconductance be? The short circuit transconductance of M1, exactly right. Let's call this M1 and this M2. So capital GM should just be GM1. All right. And this should be negative GM R out. R out is just what we see looking up. Now, the reason for that specifically here, because I saw some of your heads do a swivel, is because we're neglecting channel length modulation, right? If we did not neglect channel length modulation, we definitely have an R out looking down, and then we'd have something different looking up. Because we've been neglecting channel length modulation, though, what we see down is an open circuit. What do we see up, neglecting channel length modulation? I disagree. One over GM2. That's it. So in this case, our voltage gain would literally just be negative GM1 GM2. That's our transfer function for this circuit, neglecting the effects of channel length modulation. It would be vastly different and more complicated if we were including our effects of channel length modulation. So this is the scaling factor that we're going to apply to our capacitance, right? So if we go back here real quick to our small signal model, CGS1 would be replaced by CGS1 plus CGD1 times a factor of 1 plus GM1 over GM2. And then CY would have added to it a factor of CGD1 times 1 plus GM2 over GM1. Luke. I've been ignoring, yeah, channeling modulation.
Why wouldn't you come to the part of you didn't have to take that path on your ground?
Let's look at it. So we would have RD here. So this is our drain, right? Of 2. And then we would have GM2, VGS2, and then plus minus VGS2 like so. And then this is where we're looking in, right? So let's call this guy V test. And let's call this current I test. We okay with this? This is how we literally do it. Okay. So pretty obviously, I test is just negative GM2 times VGS2. Are we okay with that? V test is the potential difference between this node and ground, which is negative VGS2. So V test is negative VGS2. Or GM2 V test, and therefore R up is V test over I test, which is 1 over GM2. Does that satisfy your question? No, intuitively I can, yeah, no, intuitively I can see like, why the hell did we leave RD out? If we apply the test source method, this is what we get. That's what I'm going to stick with because that's how my brain works. Okay. So if we wanted to apply the Miller method, we now have our scaling factor and all that kind of good junk. So what that would do would effectively associate a single capacitance with node X and resistance, a single capacitance with node Y, and a single capacitance with our output node so that we could effectively find a pole associated with each of those three nodes, which would be a good estimation of our horrifying looking transfer function. I believe I'm going to have you guys do that for a homework problem. Again, largely because I don't trust myself to do good math right now. All right, so this was a rather terrible explanation of the high frequency response of cascode amplifiers. Let's do something that I can more easily wrap my brain around. Let's look at a differential pair. So for our high frequency response of our differential pair, and again, we're only going to look at high frequency response because we're dealing with an integrated circuit. We would have something that looks like this. So we're biasing it with some resistance RD. Here is our transistor M1. Here is our transistor M2. Here is VN1. Come way over here for VN2. And then here is our tail current ISS. So this is our bare bone system. Now let's start throwing in our capacitances. So between our gate and our drain for M1, we would have CGD1. Between our gate and our source for M1, we would have CGS1. Between our drain and our bulk, we would have CDB1, and I'm going to call this guy out here B out 1. Between our source and our bulk, we would have CSB1. And then we would have the exact same thing mirrored on the right-hand side of the circuit. So CDB2, CGD2, CGS1, and finally CSB1. All right, so let me ask you guys a very important question here. Is this circuit symmetric? So that means that we know that this node is a small signal ground, right? Because when we have a symmetrical circuit, this floating potential in the zero has to exactly balance out. All right, so here's my axis of symmetry. If we were to look at only a half circuit here, what would we have? Right. But yeah, we'd have a very simple common source amplifier to analyze, right? CSB1 would be canceled out. because it's grounded on both sides. So if, let's draw this. Right. So we would have VDD, RD, VN1, CGS1, CGD1, CDB1. Here's the out. So we would have two options in determining our high frequency model for this guy. Okay. The first of which is a direct method where we would have to take into account that our gate and our drain are linked together by that capacitor CGD1, which every other time we've analyzed anything like that has given us a second order system, or excuse me, a second order polynomial to deal with. So that would be extraordinarily similar to what our analysis looked like for our the direct analysis of a common source amplifier, right? Because let's see, the only difference really that we would have is that our our RSIG in this case is 0 or short circuit. So we've absolutely analyzed that before. Or we could use the Miller technique to split up this capacitance CGD1 and have some of it in parallel with CGS1 and some of it in parallel with CDB1. What would be our transfer function between our gate and drain node here? It's a common source amplifier. What's the? Like the most basic common source amplifier. Negative GMRD. Like the basic common source amplifier gain, because that's all this is when we take the capacitors away. It's just a common source amplifier, like the most basic variation. No degeneration or anything like that to worry about with at all. So just to be extraordinarily clear, AVXY in this case is literally just negative GMRD, which is exactly what it was when we looked at just a simple common source amplifier earlier. Okay. So despite the fact that we have this big ugly circuit, because it's perfectly matched, effectively all of the poles on the left-hand side and all of the zeros on the left-hand side are going to be exactly the same as all of the poles on the right-hand side and the zeros on the right-hand side. So from a high frequency response, it's going to behave identically to a common source amplifier, which we spent literally over a week describing. All right, I think that's enough out of me for today before I screw anything else up. So this is our last bit for our frequency response, okay? I will gear your test very specifically to not include anything that we talked about today, because I feel like I screwed it up pretty hard. I will rewrite some notes and upload it so that you have some relevant information about it that I feel less shitty about, but I don't feel that it would be appropriate for me to test you on stuff that I feel I did a very bad job of explaining to you. So your exam will only be covering common source amplifiers, common gate amplifiers, and source follower amplifiers. Your test very specifically will only have MOSFET circuits. On Friday's content will be about feedback amplifiers. So that's moving into the next topic. So please show up. But it will not be relevant for the exam.
Oh,
That
no
sound-
review.
It was not my intention to do a review, and I actually don't know that we have time to do a review if I want to cover everything about feedback amplifiers that I want to. I feel, other than today, that we've beat these concepts pretty well to death in as much as the different methods that you would use to describe everything, or to the different methods that you would use to analyze literally any circuit I could possibly give you. If you have questions about stuff, though, I will be in my office literally all day tomorrow, and I'd be happy to answer questions for anybody that felt the need to stop by.
Okay, that's what I was gonna ask.
Okay? Anything else? All right. So homework 4, I have the numerical solution for problem 3A and 3B. I haven't done 1 or 2 yet, but that's literally, I just need to put my equations into MathCAD, and I have not yet done problem 4 yet, but I will try to work on that this afternoon some. So I hope to get those up to you, as well as your homework assignment on the rest of the amplifiers up tonight. So I have absolutely begun the laborious process of writing my crazy shit down. Any other questions? All right. Again, see you guys on Friday. Sorry for the confusion.